Today, I will present you about details of geodetic airframe. First of all, let's get to know the history of geodetic airframe first. A geodetic airframe, or basket weaved, is an aircraft structure developed by British aeronautical engineer named Barnes Wallis, but sometimes spelled as geodesic. Previously, Professor Schultz was used for the Schultz-Lanz airship SL-1 in 1909. The earliest known use a geodetic airframe design for any aircraft was for the pre-World War I Schultz-Lanz SL-1 rigid airships envelope structure in 1911. With the airship capable of up to 38.3 kilometers per hour or 23.8 miles per hour top airspeed. And here's a picture of Schultz-Lanz SL-1 that we talked about a while ago. Most of them are made of plywood instead of aluminum alloys. This airship was built by the Luftschiffbau Schultz-Lanz company from 1909 to 1917. Then there is airplane named Letecoe 6 was a French four-engined biplane bomber of the early 1920s. It was of advanced ornamental construction and probably the first aeroplane to use geodetic construction. Only one was built.
The meaning of geodetic airframe. Geodetic airframe is a space trusses connected transversely form a spiral crossing basket weave-like pattern, which gives it a strong and flexible property. Additional to those properties, geodetic airframe is also light and hollow, which allows you to have more feel and payload. For material that we use as geodetic airframe in Barnes-Wallis bomber, which consists of 1,650 components, are duralumin W-shaped beam and linen. Duralumin is one of the earliest type of aluminum alloy, which consists of 91 to 95% of aluminum, 3.8 to 4.9% of copper, and other elements. Although today it is referred to aluminum copper alloy designated as 2000 site series, as 2014 and 2024 alloy. And linen is a textile made from the fibers of the flax plant. It is very strong, absorbent, and dries faster than cotton. The geodetic airframe is so strong that the Wellington bomber that used the airframe were damaged on the rear multiple times, result in burn of linen and exposed airframe, but is still able to fly back.
Later, it will be about Van Wallis' geodetic airframe. He was inspired by the experimental use of geodetic force distribution on 100 airships, first flew in December 1929 by return crossing of Atlantic, and in 1930 the R100 was broken up for scrap. There is also a bomber developed using the principle of Barnes-Wallis geodetic airframe. Example: Vickers-Wellesley. The Vickers-Wellesley was a medium bomber that was designed and produced by the British aircraft manufacturer Vickers Armstrong. The Wellesley was developed during the early 1930s, designed to perform the bomber role only, and its use of the type as a maritime reconnaissance aircraft during September 1942. Next, Vickers Wellington was a British twin-engine long-range medium bomber It was designed during the mid-1930s, led by Richard Armstrong, chief design person. A key feature of aircraft is its geodetic airframe fuselage structure, which was principally designed by Van Wallis. Next, Vickers was a multi-purpose twin-engine British aircraft developed from Vickers Wellington, and the Wallis was the largest British twin-engine aircraft to see use during the Second World War. And finally, Vickers Windsor. The Vickers Windsor was British four-engine heavy bomber, designed by Van Wallis and Rex Person. The Windsor used Wallis geodetic body and wing structure. In this aircraft, the wing structure flexural strength in bending and torsional stiffness were calculated as being controlled separately by a single spar and the geodetic lattice construction respectively. However, testing of wind showed that the geodetic structure also contributed to the wing bending resistance. So for the Windsor, Wallis designed the wing so the geodetic structure would take out the torsional and bending load. It was achieved.
From the whole story, that is the spiral frame is connected transversely, which causes the force to be countered. Starting from the monocoque shape, it is unable to bear the concentrated load. The solution is you can be drilled through the structure, which increases flexibility, provides better cushioning, but reduces the ultimate strength of the geometry, which can only be solved by increasing the thickness of the geometry to increase ultimate strength while maintaining the desired flexibility. The geodetic structure is the only development of the monocoque perforation method, which is more economical than other methods clearly. Thanks to listen.